So, in the 17th and 18th century, there was this guy named Newton, whom you may have heard of. Newton essentially invented modern physics as we know it. Anyway, this guy made and organized laws of motion and said that they would be true for anyone in an inertial reference frame. An inertial reference frame is a point of view for someone moving at an unchanging speed and direction, not speeding up or slowing down, like, say, maybe a moving train. If you had one person on a moving train that was moving perfectly at one speed, and one person on a still train relative to the Earth's surface, without looking out of the train, neither one would know if they were moving or not, relative to the Earth. Both people can take all kinds of measurements and discover the same laws of physics for inside their respective trains. But if we have someone on a train that is speeding up with some acceleration, a non-inertial reference frame, then inside their train, everything will slide to the back and they will be pressed against their seat. If this person were to invent laws of physics for the train, they would discover that everything moves to the back if you don't nail it down. Now, if they knew that this is not a normal law of physics for an inertial reference frame, then they could know that they are accelerating and are hence in motion. Later, physicists discover that light has a speed and get a rough idea about how high it is. This will be important in a moment. Then comes along this Einstein fellow, another guy you might have heard of. Einstein likes Newton's statement about inertial reference frames, but it is revealed that light having a speed actually conflicts with it. If you have on both your moving train and your still train a lamp, and you tell the person on the train to put the lamp at the other end of the train, flick it on, and measure the time it takes for the light to get to themselves, and hence measure the speed of light, which is hard but not impossible, there will be a fundamental problem. The person on the moving train will measure the speed of light to be a different speed, or so is thought. If, say, the lamp was at the front of the moving train and the rider was at the back, when the lamp emits a light particle, it will be moving towards where the person was at the speed of light, but the person is also moving towards the particle of light at the speed of a train. This would mean that the light would take less time to get to him or her, and he would think that light had a faster than normal speed. If they look at each other's measurements, then they can determine that at least one of them was moving. This must be wrong. How could Newton be right about everything but light? This was a core idea in physics that a lot of people held very dear to concepts at the time, and the undermining of this was really an undermining about how people thought about physics. It didn't make any sense to people, and it conflicted with how people thought about physics. Many physicists suggested solutions to the problem, but Einstein thought that they were all silly and unnecessary. Einstein simply postulated. He assumed, really guessed, that all observers at any speed will measure light to move at the same speed. Light will have a constant speed even if you're moving towards it or away from it. And that fixes the problem, but it reveals a bunch of new and weird things that comes with that were eventually shown, so far, to be accurate. Okay, so let's say we're dealing with this guy in the train again, and he doesn't know he's in a train, he doesn't know he's moving down this track at some velocity, v, and we have some guy on the outside, on a rock, and he can, there doesn't need to be an arrow there, he can see that this guy is moving down this track at v, but the guy inside, he doesn't know what's happening. Now, they both have a stopwatch here, and the one in the train also has something called a light clock. That's this thing here. Now, what is a light clock? Well, a light clock is essentially a very, very simple form of telling time, where you just take one particle of light and two mirrors, and you just shoot that particle of light somehow, and it just bounces up and down and up and down and up and down and up and down. Let's say that's 8 bounces, and that's how you tell the time. You say, oh, this thing took 8 bounces of time, because it takes a certain amount of time for the light to travel that distance. Now, let's make up some kind of law of physics for this certain light clock. Let's say, for a particle of light, it takes 1 second to go from the bottom to the top. And that's a fundamental law about it. When you have this in a non-inertial reference, in an inertial reference frame, the light takes 1 second to go from the bottom to the top. Alright, so this guy here, right, because the whole thing that we're talking about is that, the whole thing that Einstein is defending here is that this guy will measure the same laws of physics as this guy. And this is a known law of physics to both of them. So this guy, he can't know he's moving. So the laws of physics will be the same. So he'll just see this thing bouncing up and down, just normally, and it will take 1 second in his stopwatch for it to go from the bottom to the top. 1 second. Now let's shift over to the guy down here. He can see where the light clock is, where it is, and where the light particle is moving to. So he can kind of interpret this in his own way. And what he thinks is, wait a moment. In the time it takes for that particle of light to go from the bottom to the top, the train will have actually moved because it's moving at some velocity. He can see that. So now we have the whole thing shifted over. Our guy inside is still happy, has a stopwatch, and this is 1 second later. At the beginning, he has a particle of light here, and 1 second later, this is 0 seconds. 1 second later, that light has reached the top. So if we draw a path, light travels in these straight lines, we will see that the light is actually moving diagonally from this guy's perspective. So that's a bit weird, because look, this distance that the person in the train saw the light travel was some distance d. Some distance d for the distance between these plates on in the light clock. But this guy, he sees, wait, it's also moving horizontally. Some distance, the velocity of the train, or the speed of the train, times time. And we can find the total distance there using the Pythagorean theorem, d squared plus v squared times t squared. All right then. So this is a weird little disagreement because this guy down here, he has to measure the same laws of physics too. That's the whole point. These people are both in inertial reference frames, so they measure the same laws of physics. So the speed of light for this guy has to be the same. So he says, wait, but that's a longer distance, and you're expecting light to travel a longer distance in the same amount of time as it takes for a short distance? No. It's a longer distance, the same speed is going to take a longer time. So let's say this guy's stopwatch, it goes by like 3 seconds instead. So for him, this whole thing takes 3 seconds, but for this guy, it seems like it takes 1 second. Does that make any sense? I mean, the laws of physics are the same. We were very careful about that. They both see correct laws of physics, but what's this weird thing about their stopwatches having different times? What if their one stopwatch is actually much slower, or somewhat slower, than the other? Why stop there? Well, why can't the whole body be slower? I mean, different parts of the body, they can be used like a stopwatch. We physically know how long some processes take, and we can say, hey, wait a moment. You know, I eat a sandwich, and I digest it in this amount of time, and look, the light, look how it's bouncing. We can do the same argument. I only digested half of my food by the time it reached the top of the rig here, while the other guy digested all of his food. So this is something called time dilation, and there's a formula for it. We're going to call the time that passes on this guy's stopwatch, we're going to call that the change in time for the guy on the train, and we're going to call the amount of time changed on this guy's stopwatch the change in time for the guy on the ground. All right? And that's going to be the same as this time here with the velocity. And there's a formula for this that I'm not going to derive due to time constraints, but you can derive it for yourself just using this expression here and this expression here, just the two distances. You can play with that and figure it out. And the final formula is that the change in time for this guy on the ground is going to be equal to the change in time for that guy on the train divided by the square root of 1 minus the velocity of that, or the speed of the train squared, divided by the speed of light as denoted with the c squared. This is the time dilation formula. And this actually applies everywhere. If you're in motion, more so than another person, at this constant velocity, time will actually move slower for you. You'll actually age slower. No matter how much faster you're moving, you will be aging slower. But it doesn't really come into any real play unless you're moving close to the speed of light. So don't count on outliving a bunch of people just because you went on that one plane trip. All right, thanks for watching.